Yes, thank you. So I'm going to speak about ontology-mediated queries and how to approximate them. And our starting point is the well-known fact that ontology-mediated querying can be rather costly. In particular, if your ontology is formulated in an expressive description logic, such as ALC or ALCI, then the complexities that you will face would typically be something like co-NP completeness and data complexity and single or even double X-time completeness and combined complexity. And clearly this is very expensive, probably prohibitive for practical implementation. And a natural reaction to this situation is to say, okay, then let's approximate. And in principle, you can do two kinds of approximation. You could approximate from below, obtaining answers that are sound but potentially infinite, or from above, and then your answers would be not infinite, incomplete. Or from above, yeah, and then your answers would be complete, but potentially unsound. Now, the second option here might look a little bit obscure, but actually it's quite natural when you combine it with the first option, when you do both kinds of approximations, because then it might happen that you obtain the same answers in both cases, which means that you have found the exact non-approximate answers, and that's, of course, an ideal situation. Now, this has been implemented in several systems, Pagoda probably being the most well-known one, Trowel and Screech slightly older. All these systems are fairly pragmatic in how they construct the approximations from below and from above. It's not really clear whether they are as complete as they can be. I guess in practice, this is reasonable. I don't want to criticize it, but here in this work, we aim to understand from a more theoretical angle this kind of approximation here. So let me make precise the aims that we have when approximating. First, we insist on having p-time data complexity. So if the approximation does not achieve p-time data complexity, then we think it is no good. But ideally, we would like to achieve more. On top of p-time data complexity, we would like to have fixed parameter tractability, with the parameter being the size of the ontology-mediated query, if that's possible. And we also would like to improve the combined complexity, again, if that's possible. So that's what we want to achieve. Now, how can we achieve it? I will start with approximation from below. So how to approximate from below? Well, let me recall what ontology-mediated querying is. It's a question, you're given an ontology and a database, and a query and a candidate answer, and you want to know whether it logically follows from the ontology and the database that your candidate is really an answer. And this gives us three potential points of attack for approximating from below. We could take into the focus the query and weaken the query. This, however, is not promising given our list of desiderata, because even the weakest kind of query you could imagine, even queries, atomic queries, which take the form of a single unary atom, result in co-NP hardness in data complexity. So this is out, and we are left with 2 points of attack, and those are both valid, and we study both of them. So you could weaken the ontology. For doing this, you would choose some ontology language L that is computationally more well-behaved than the ontology languages that you started with. So here we look in particular at Horn description logics such as ELI bottom and ELIU bottom. The U is not really that standard as a notation. What I mean here is the universal role. And we will also look at tuple generating dependencies, more precisely at frontier one tuple generating dependencies, which means that at most one variable is shared between the body and the head of each rule. And in addition, we impose bounds on the tree width of the body and the head of the TGDs. Okay, but whatever L you choose, once you have chosen it, you can define L ontology relaxing approximations. So you have your original ontology-mediated query to be evaluated on some database. And then how do you approximate? Well, you replace the original ontology with new ontologies, O prime, that are formulated in the more inexpressive language L that you have chosen, and that must be logically implied by the original ontology. And you consider all such O prime and then take the union over all answers. Okay, this is the semantics of ontology relaxing approximation. You could object now that there will in general be infinitely many such O prime, and that's true, but this is only defining a semantics. We don't insist on all these O primes being materialized for computing the answers. There are better algorithms, more direct ones, where you don't have to consider this infinitely many O prime explicitly. Okay, let's go to the third option. The third option is to focus on the database, to weaken the database when you approximate. So here you should start with choosing a class of databases D for approximation that are computationally better behaved than the class of all databases. And we look here at tree-shaped databases and at databases of tree expanded by some constant K. And again, for such a class D, you can now define D database relaxing approximations. Here you leave your ontology-mediated query as is. You don't touch the ontology. It remains in the expressive language. But now you replace the given database D with a new database D prime from your class, subject to the condition that it has a homomorphism into the original database D. You consider again all D prime and take the union. Again, there are infinitely many choices for D prime in general, but that's not really a problem. Okay, that's the setup that we study and that we actually propose in this paper, this formalization of approximation. Now let me speak a little bit about results. So we have two kinds of results. The first one is about relative completeness, when you approximate via the ontology or via the database, and then with different languages and different database classes. There are many different kinds of approximations that emerge, and we are interested in their relative completeness. I cannot present you all results that we have. Here are just a few. First one is something very basic. I had mentioned that we look at this logic ELI with the universal role, and I want to tell you why we do that. That's because it turns out to be more complete than ELI without the universal role. Somewhat interestingly, because the universal role was not present in the languages that we started with. And there's another reason. So computing the approximate answers is much easier to understand if you have the universal roles, and therefore we actually don't look at this language, only at the one with the universal role here. Here's another observation. If you increase the tree width of the body and heads of your TGDs or of the databases, then this increases completeness. So we can show that in both cases, there are actually infinite hierarchies of more and more complete approximations. And then it's of course interesting to compare ontology relaxing approximation with database relaxing approximation. Here it's ELIU versus tree databases. How they relate, that depends on the queries in which you're interested. If it's atomic queries, then tree database relaxing approximation is actually strictly more complete than ontology relaxing approximation. If you go to more expressive logics, such as conjunctive queries, then they become orthogonal. You can do the same on the level of TGDs and bounded tree width databases. The picture is even more subtle. I cannot give you any details. I can only tell you it depends on many parameters, such as the tree width of the queries that you're interested in, on their arities, and UCQs even behave differently from CQs. Okay, there are more results of this kind in the paper, and also many, many concrete examples that show what these approximations do and what they don't do. And then the second class of results that we have is, of course, complexity results. Let me start with ontology relaxing approximations, still from below. So here I have the description logic ELIU as the approximation language. Here it's TGD. It's just complexity results again without approximation. But instead of going through all the fields in this table, let me just give you an executive summary, so to speak. So with ontology relaxing approximation, there's good news. We always achieve p-time data complexity, so our main desideratum is satisfied. There are very relevant cases where we additionally achieve fixed parameter tractability or even linear time data complexity. So in particular, we achieve FPT here if you ask conjunctive queries or unions thereof of bounded treewidths, and we achieve linear time data complexity for atomic queries. And it also reduces the combined complexity. So you go down from double X time to X time, which is of course still high, but also a significant reduction. Then let's go to database relaxing approximations. Here's that table. The good news is it also always achieves p-time data complexity, even always fixed parameter tractability. So in this respect, it is even better than ontology relaxing approximation, but it is not so good regarding combined complexity. In fact, there are quite interesting effects that sometimes it increases, the combined complexity increases. So for example, here, when you have ALC ontologies and UCQs, and you approximate using, for example, tree databases, you go up from X time to double X time. So you become simpler in data complexity, but harder in combined complexity. So my overall feeling is that these ontology-based approximation notions are to be preferred. I have 1 minute, only a quick glance at approximation from above. There are obvious duals for defining approximations from above. You can just, for ontology strengthening approximation now, you can just reverse the direction of implication. For database strengthening approximations, you can reverse the direction of homomorphisms. So the notions are very naturally defined also from in the version from above. We don't have that exhaustive results in this case, as in the case from below, but we have some first results, and they are very interesting, I think. So let me start with ontology strengthening. With ontology strengthening, we do always achieve FPT, but we again have the effect that the combined complexity goes up from X time to 2X time, even now in very, very simple cases. And the last thing I want to say, for database strengthening from above, yes, this is very problematic. So here we even have a case that is actually tractable. The original language has p-time data complexity. Yeah? So if you do not approximate, you have p-time data complexity. But if you approximate in terms of tree databases, you go up to intractable, to co-NP completeness in data complexity. So this is probably nothing you really want to use as an approximation. Thank you very much.